Thermosiphon is a physical effect and refers to a method of passive heat exchange based on natural convection, which circulates a fluid without the necessity of a mechanical pump. Thermosiphoning is used for circulation of liquids and volatile gases in heating and cooling applications, such as heat pumps, water heaters, boilers and furnaces. Thermosiphoning also occurs across air temperature gradients such as those utilized in a wood-fire chimney, or solar chimney. This circulation can either be open-loop, as when the substance in a holding tank is passed in one direction via a heated transfer tube mounted at the bottom of the tank to a distribution point even one mounted above the originating tank or it can be a vertical closed-loop circuit with return to the original container. Its purpose is to simplify the transfer of liquid or gas while avoiding the cost and complexity of a conventional pump. Simple thermosiphon. Convective movement of the liquid starts when liquid in the loop is heated, causing it to expand and become less dense, and thus more buoyant than the cooler liquid in the bottom of the loop. Convection moves the heated liquid upwards in the system as it is simultaneously replaced by cooler liquid returning by gravity. Ideally, the liquid flows easily because a good thermosiphon should have very little hydraulic resistance. Heat pipes equals. In some situations the flow of liquid may be reduced further, or stopped, perhaps because the loop is not entirely full of liquid. In this case, the system no longer convects, so it is not a usual thermosiphon. Heat can still be transferred in the system by the evaporation and condensation of vapor. However, the system is properly classified as a heat pipe thermosiphon. If the system also contains other fluids, such as air, then the heat flux density will be less than in a real heat pipe, which only contains a single fluid. The thermosiphon has been sometimes incorrectly described as a gravity return heat pipe. Heat pipes usually have a wick to return the condensate to the evaporator via capillary action. A wick is not needed in a thermosiphon because gravity moves the liquid. The wick allows heat pipes to transfer heat when there is no gravity, which is useful in space. A thermosiphon is simpler than a heat pipe. Single-phase, thermosiphons can only transfer heat upward, or away from the acceleration vector. Thus, orientation is much more important for thermosiphons than for heat pipes. Also, thermosiphons can fail because of a bubble in the loop, and require a circulating loop of pipes. Reboilers and colandria equals, if the piping of a thermosiphon resists flow, or excessive heat is applied, the liquid may boil. Since the gas is more buoyant than the liquid, the convective pressure is greater. This is a well-known invention called a reboiler. A group of reboilers attached to a pair of plena is called a colandria. The term phase change thermosiphon is a misnomer and should be avoided. When phase change occurs in a thermosiphon, it means that the system either does not have enough fluid, or it is too small to transfer all of the heat by convection alone. To improve the performance, either more fluid is needed, or all other fluids should be pumped out of the loop. Solar energy. Thermosiphons are used in some liquid-based solar heating systems to heat a liquid such as water. The water is heated passively by solar energy and relies on heat energy being transferred from the sun to a solar collector. The heat from the collector can be transferred to water in two ways, directly where water circulates through the collector, or indirectly where an antifreeze solution carries the heat from the collector and transfers it to water in the tank via a heat exchanger. Convection allows for the movement of the heated liquid out of the solar collector to be replaced by colder liquid which is in turn heated. Due to this principle, it is necessary for the water to be stored in a tank above the collector. Computing. Thermosiphons are used in computing to describe a system for water cooling the internal computer components, most commonly referring to the processor. While any suitable liquid can be used, water is the easiest liquid to use in thermosiphon systems. Unlike traditional water cooling systems, thermosiphon systems do not rely on a water pump but rely on convection for the movement of heated water from the components upwards to a heat exchanger. There the water is cooled and is ready to be recirculated. The most commonly used heat exchanger is a radiator where air is blown actively through a fan system to condense the vapor to a liquid. The liquid is recirculated through the system, thus repeating the process. No pump is required. The vaporization and condensation cycle is self-sustaining. Uses equals, modern processors get relatively hot. Even with a common heat sink and fan cooling the processor, operating temperatures may still reach up to 70 degrees Celsius. A thermosiphon can handle heat output at a much wider temperature range than any heat sink and fan, and can maintain the processor 10-20 degrees Celsius cooler. In some cases a thermosiphon may also be less bulky than a normal heat sink and fan. Drawbacks Thermosiphons must be mounted such that vapor rises up and liquid flows down to the boiler with no bends in the tubing for liquid to pool. Also, the Thermosiphone unregistered trademark S-fan that cools the gas needs cool air to operate. Engine cooling. Early cars and motor vehicles used thermosiphon circulation to move cooling water between their cylinder block and radiator. As engine power increased flow was required, and so engine-driven pumps were added to assist circulation. More compact engines then used smaller radiators and required more convoluted flow patterns, so the circulation became entirely dependent on the pump and might even be reversed against the natural circulation. An engine cooled only by thermosiphon is also very sensitive to low coolant level, that is, losing only a small amount of coolant stops the circulation. A pump-driven system is much more robust and can typically handle a lower coolant level. See also, convection, geothermal heat pump, heat pipe and loop heat pipe, passive solar, reboiler, siphon, solar heating, thermic siphon, vapor compression refrigeration, water cooling. Thomas Fowler. References: Thermosiphon technology for artificial ground freezing. Makers.com. Holubg, flat loop thermosiphon foundations in warm permafrost. Ptsolar.com, thermosiphon heat exchangers. Apogee.net. What is a heat pipe? Other topics, articles, chemical engineering, front page, chairresources.com. chairresources.com community. Brian Norton Solar Water Heaters, a review of systems research and design innovation, Green. 1, 189-207, ISSN 1869-8778, Kuemel, Bernhard. CPU vapor cooling thermosiphon. http, www.overclockers.com/ Retrieved August 26, 2012. External links. Definition of thermosiphon, another definition of thermosiphon, HP Labs report on thermosiphons for computer cooling, antique thermosiphon engine cooling.